These days, the problem is not a shortfall of data, but rather knowing how to correctly analyze the mass of data that is available. Now, as an analyst, you need to know which data it is that you need in order to answer the question posed to you by the stakeholders. You need to accurately analyze the data in order to draw conclusions from the analysis and be able to clearly and concisely convey your findings. So as you can see, we have a long but exciting road to go to become successful analysts. Hello everyone, and a warm welcome back to Shaw Academy. For those of you that missed lesson 1, Marlies is your educator, and she created this course with the aim of introducing you to statistical analysis. Her goal is for you to be comfortable with statistically analyzing whatever data challenge you might be faced with, and do so accurately. Marlies has an undergraduate degree in computer science and a postgraduate degree in mathematical statistics. She has also completed the official SAS-based certificate course. Marlies enjoys extracting insights from data, particularly medically related data, which is why this lesson will be medically themed. George Bach said, "All models are wrong, but some are useful." So stay tuned to find out what this means. Just to remind you, my name is Nina Smith, and I am the presenter of this course. This is your professional diploma course in Statistical Analysis Lesson 2, Understanding the Data. Today's lesson will be all about study design, data types, and a sneak peek into summarizing data. Understanding the study design and the type of scales that are used to measure data is a crucial step in analyzing the data accurately. Only after we know the pros and cons of the way the data was gathered can we start describing the data. Okay, let's kick off this lesson with our first topic of the day, study design. Now, as I've mentioned before, Marlies loves all things medically related. Therefore, this topic will be a medically inspired one. So, what is study design, you might be wondering? Study design can be seen as the framework of research, each with its own advantages and disadvantages. We use the study design to help us answer the question posed to us by the stakeholders. We can also describe study design as a structure or set of procedures that we use to gather and analyze data. We can divide the study designs into two groups, observational studies and experimental studies. Now, an observational study is a study where researchers observe the effect that, for instance, risk factors or diagnostic tests have on, for instance, the patient, without trying to make changes to exposed patients. And an experimental study is when we introduce an intervention to the group of patients and evaluate the effect that the intervention has on the group. We can divide observational studies into 4 main types: descriptive, case-controlled, cross-sectional, and cohort studies. Let's investigate each of these observational studies in a bit more detail to evaluate the impact of the study design on the data collection and the analysis process. When we describe specific characteristics of a group of patients in a report, it is called a case series study. A case-controlled study is more often over a shorter period of time. For example, a 1997 study introduced a group of 40 patients with information considering stroke, transient ischemic attacks, or corroded bruits. The researcher wanted to differentiate between 2 methods to see which is better at predicting peak systolic velocity. This study therefore had no control group or hypothesis. The study was meant as a precursor to other studies. Descriptive studies is therefore one of the simplest study designs and is often a precursor to other studies that would then subsequently be investigated in a case-controlled cross-sectional or cohort study. Case-controlled studies, on the other hand, begin with the lack of an outcome and look backwards to try and recognize possible causes or risk factors. Case-controlled studies can be used for example, causes of a specific disease, whereby individuals will be chosen on the basis of having the disease. The control group would be individuals not having the disease. Now, the history of both groups are then evaluated to try and find the risk factors involved in the cases of the patients that have the disease in comparison to those that do not. Case-controlled studies span over a longer period of time than descriptive studies. The third type of observational study design we will delve into is cross-sectional studies. Now, this study design is also known as survey studies, prevalence studies, and epidemiological studies. Cross-sectional studies analyze data on a group of subjects at a specific point in time rather than over a period of time. For example, if the researcher wants to learn more about the relationship between demographic information and trauma patients' identification with elevated blood alcohol levels, they could choose a specific time of day, gender, and age group to investigate and create 3 models based on a variety of these factors. We use a cohort study when we have a group of patients that have characteristics in common and who remain part of a group over an extended period of time. Because we are evaluating events that will happen after the study has begun, this study is prospective in nature. For example, the researcher might want to evaluate the cause of an incidence of a disease. We want to know what will happen to the group of patients. The researcher could evaluate a group of patients with, for example, hypertensive cardiovascular disease, and like the 1970 study of Gordon and Cannell, then conduct a comprehensive 20-year follow-up. This could lead to identification of the risk factors for these patients. In fact, journal articles have been written about this cohort study, and some of the children of the study are now being followed as well. Experimental or clinical studies that involve humans are referred to as clinical studies. The purpose is to draw conclusions about a specific treatment or procedure the patients are undergoing. Experimental studies can be either controlled, for example, when one drug is compared against another, or uncontrolled, for example, when the researcher describes the experience of the experimental drug or procedure, but it is not compared to another. A controlled trial, as mentioned, is when the researcher compares one procedure or drug to another. This could be a placebo or a previously accepted procedure. The researcher wants to determine whether the intervention will be different to the accepted procedure. Now, controlled trials can be concurrently controlled, where one group is the experimental group and the other the placebo or controlled group. These 2 groups are treated the same, except for the procedure's difference itself. Controlled trials can also have sequential controls or external controls. Our last study design we will discuss for today's lesson is studies with no controls or uncontrolled studies. Now, these studies are not by exact definition experiments or trials because they do not have interventions with controls, but are useful nonetheless. For example, the 1997 study of Crook and Associates described the results of a trial of radiotherapy for prostate carcinoma in which patients were followed for a minimum of 12 months and a maximum of 70 months after the procedure. The researchers' aim was to determine how long patients had no repeating tumors, as well as how long the patient survived. So this was an uncontrolled study because there were no comparisons with patients treated in another manner. Even though we're having so much fun, let's not forget our assistant Morpheus. He is Shaw Academy's artificial intelligence bot and is available to you throughout the lesson. Don't forget to send your questions and answers through Morpheus. Rating every answer will also help to ensure we improve him. As mentioned in Lesson 1, you will be able to access your summary notes and webinar slides from your course page under your toolkit. These will come in quite handy for your assignment at the end of this module. After each and every lesson, you can take the lesson quiz. Here, we will ask you some general questions to improve the quality of the information we give you, and we'll also test your knowledge on the lesson you just watched. If for whatever reason Morpheus or your classmates are not able to assist you with an answer, please send us an email at support@shawacademy.com and we will make sure to get back to you as soon as possible. Okay, for the second topic of the day, we are going to investigate different types of data and learn the importance of correctly identifying each. Data can be either quantitative or qualitative. Quantitative data is typically measures of values and denoted with numerical values, whereas qualitative data is measured by different types of data such as names or symbols. Qualitative data is non-numerical data that can be collected through interviews like focus groups. Typically, qualitative data is gathered from open-ended questions, and it is subjective. We can use this type of data to generate the hypothesis and answer the why to our question. Quantitative data, which we will work with in this course, is numerical, and it is collected through sample sizes that are typically bigger than that of qualitative data. Quantitative data is more objective than qualitative data. It is drawn from questions that are typically more closed-ended, and we use quantitative data to validate our hypothesis. Scales of measurement refer to ways in which variables or numbers are defined and categorized. Each scale of measurement has certain properties, which in turn determines the appropriateness for use of certain analysis. In this course, we will subdivide scales of measurement into 3 common categories, namely nominal, ordinal, and numerical. The nominal scale of measurement is seen as the simplest level of measurement. Data is nominal when the values are words describing categories. Their values can also be referred to as the naming or labeling variables. This data type needs a minimum of 2 categories. It is also not ordered or ranked. This data type is best represented by a pie chart or a bar graph. Examples of this data type include gender, so male or female or other, and for example, marital status, so married, unmarried, divorced, partnered, single, and so forth. An inherent order exists among categories of ordinal data. Data that is ordinal is very similar to nominal data, but the category items can be ordered or ranked to be less than or greater than the other. It is best represented by a box plot. Now, an example of this type of data includes rankings for athletes. Athletes may be ranked as first, second, or third. However, we do not know how far the first athlete won, merely that they won. The last scale of measurement we will introduce in this course is numerical. In this type of scale, the difference between the observations carry meaning on a numerical scale. This scale is sometimes referred to as quantitative observations. The 2 types of numerical scales are continuous and discrete. Continuous scales measures numbers on a continuum, and a discrete scale measures numbers equal to integers, for example, as number of fractures. So, why are we interested in scales of measurement? Why is this an important concept to us? Well, we use specific statistical methods with specific scales of measurement. For example, you have to analyze continuous data differently than categorical data. Otherwise, it would result in a wrong analysis. Therefore, knowing the types of data you're dealing with enables you to choose the correct method of analysis. Furthermore, we also need to know which data type or scale of measurement we're dealing with to choose the right visualization method. Think of data types as a way to categorize different types of variables. In the next lesson, we will continue summarizing data by exploring measures of dispersion or spread, together with visualizations for categorical and continuous data. Now, this will be a practically inclined lesson, so be sure that you grasp today's measure of central tendency before advancing to the next lesson. Congratulations, you've made it to the final topic of the day. We will now begin exploring some of the various ways we are able to summarize data. starting with measures of central tendency. Summarizing data helps us make sense of the mass amount of information that we have collected. Some useful information starts emerging when we indicate how the center of the distribution looks like. These numbers are collectively referred to as measures of central tendency. These three measures of central tendency include the mean, the median, and to a lesser degree, the mode. These measures are all used for numerical data, with the median also being used for ordinal data. The mean is the sum of the observations divided by the number of observations. In the formula, the Greek sigma means to add or sum. X represents the observations and n the number of observations. It is also known as the arithmetic mean of the observations. The mean is not used for an ordinal scale and is sensitive to outliers or extreme observations. The median is known as the middle observation or the 50th percentile. The median is the point where half of the data will be smaller than the observation and half of the data will be larger than the observation. There is no standard symbol for the median, but some sources refer to it by M or MD. We arrange the observations in the sample from smallest to largest and choose the observation in the middle as the median value. The median is less sensitive to outliers than the mean. The mode represents the numbers that appear the most frequently or the observations that are the most commonly occurring. The mode is also known as the modal observation, and when a set of observations has two modes, it is called bimodal. We more commonly use the mode when dealing with qualitative information. The mode is also not affected by extreme outliers. Let's pop over to SAS University Edition now and start exploring our open source dataset from Kaggle. In the previous lesson, we imported the wine quality dataset from Kaggle. Now we will be conducting some descriptive measures on the wine quality dataset now. Remember that we stored this file in the My Folder subfolder we created? Also remember that we are able to view that automatically created code from SAS in the code pane at the bottom of the screen. The data set is created in the temporary library of SAS called work, and the name of the temporary data set is import. Let's create a new program. You can click on the SAS program feature or use the key F4 to create a new SAS program. Here we have a blank scripting pane. We will use the proc means function of SAS to draw descriptive statistics from the data set. Now, proc is short for procedures. SAS shows us that every proc command begins with the keyword proc. That is a required element. Once the name of proc is specified, you may then specify one or more options available in proc in any order. According to the SAS documentation, the means procedure is one of the most powerful and flexible procedures you'll find in the SAS system. You can use it to rapidly and efficiently analyze the values of the numeric variables and place those analyses either in the output window or in a SAS or SAS dataset, or both. 5 default measures are supplied with this procedure, and we will evaluate those in a few seconds. Now we need to tell SAS where the data lies, so we say that the data is equal to the temporary import dataset created in the previous session of SAS. Oops, there is an error. The reason this is happening is because we imported this data set in the previous SAS session. Therefore, as you can see, SAS tells us that the data set does not exist in the work folder anymore. We need to therefore run the previous script again in order for SAS to store the data in the temporary work library again. And once we have done that, SAS will be able to compute the proc means statement without any errors. Now that the proc means has successfully run, we are able to view the result in the results pane. The means procedure shows us the amount of variables, the means for the variables, the standard deviation, the minimum and the maximum values. We are already able to draw some initial insights from the data. we can see that there are certain variables that lie between 0 and 1, and that the number of observations contained in the dataset is 1,599 with 13 numerical descriptive variables. Okay, if we navigate back to the Kaggle site where we downloaded the dataset from, we can read a little more about what each of these variables represent. Something interesting that Kaggle recommends is categorizing the wine quality scores into good and bad scores. We can look at this in future lessons, but for now, let's navigate back to the SAS Studio. Okay, maybe we don't want to view all the variables' descriptive features in the results now, because they are not relevant to us. By inserting the var command with the variable names we want to view, we are able to view specific variables in the results. Now we have specified to SAS that we only want to view the proc means result of the alcohol variable. Furthermore, we are also able to view the results by class or by group of a specific variable. So say we want to view the outcome variable, qualities per score group. We can easily achieve that with a class statement in SAS added to the proc means procedure. Okay, so now we can see the results are separated per score of the quality variable. We can also see that the lower quality scores have fewer amount of observations in comparison to the quality scores in the middle of the scale, like the scores 5, 6, and 7. The higher quality scores also have a lower amount of observations in the group. Now, the last addition to the proc means procedure we will discuss for today's lesson is sorting the variable results in ascending order. We specify to SAS by which variable we want to sort. So let's say quality. Then we have to import the proc step above the proc mean step so that SAS knows which variable we will sort on. And it's as easy as that, so you can see that learning SAS is quite painless, and with only a few lines of code, we are able to extract lots of useful information from the data already. Remember, all the summary notes and slides are available in your toolkit and would really be worthwhile to keep as a resource at your fingertips beyond this course. But no sneak peeks. The lesson notes will only become available after you have attended your class or caught up with the lessons. Your toolkit will also help you prepare for your first weekly assignment, which will be a recap of lesson 1 and 2. While these assignments are not for marks, they will help you prepare for the final module assignment. Just a little hint. Some of the questions in your final assignment may look familiar if you've done these weekly assignments. Remember, you can always change your class date and time so it is convenient for you. And should you feel the need, you can restart the course, or you can watch a lesson to reference back to it at any time. Remember that the flexibility of online learning is that you can do it your own way. You can attend your classes using your smartphone, through your computer or laptop, or on your tablet device. For this week's lesson challenge, I want you to evaluate the study design of the wine dataset we've been evaluating. What study design do you think this dataset has? Does the study design impact the way we evaluate the information drawn from the data? Well done on completing lesson 2 and for progressing this far in your analyst journey. Remember to practice what you've learned in lesson 2 and to join in for lesson 3. Still here? Wondering what George Box's quote, "All models are wrong, but some are useful" meant? We can consider this quote not just in the statistical field, but in the broader scientific field as well. This aphorism accepts that statistical models will always fall short of the complexities of reality, but can still be of use. Simply put, we strive for progress, not perfection.